determination to perform better in the second test. I am very happy to see that, and hopefully we can all improve our performance. And especially, I feel very excited today. Okay? So you guys want to do better, that put some more pressure on me as well. So I want to do better as well. So we are still doing our double integration. So this is generally what we're doing here. Okay? So we want to evaluate the double integral. We're already here, I'm calling it the intervening region, right? So F here is the intervening function. All of our discussion, okay, is surrounded in identifying the intervening region. Okay? So this is the key point here. So we want to see how we can evaluate a double integral when this intervening region is given by special types. Right? So the first easiest type is this rectangle, where R is equal to X is bounded by AB, Y is bounded by CD. Basically, X and Y are both bounded by two real numbers, right? And the region is given by a rectangle. And this is the easiest case, not only because the intervening region is simple, but also we can simply write down this double integral as two single integrals and with interchangeable intervening order, all right? So we can interchange the order freely as we want. Fxy dx dy, which is also equal to from A to B, from C to D, and xy dy dx. Okay, as long as we can write it as iterated single integrals, everything will follow single variable calculus. And the last class, I was asked about one homework question. So I want to quickly practice this one. So 1, 9 from 0 to 4, square root of x divided by y dx dy. Okay? So as I said, all our discussion is surrounded by discussing this intervening region. Once we can write down it as an iterated integral, the following work should be all single variable calculus, which is not our main concern, but you gotta have to have that skill. Okay, so we're not gonna teach how to do single variable calculus in this class. So this is one exception. I wanted to practice a bit. Okay. So first of all, as long as I have this, I know this is a rectangle as the intervening region. Right? It's pretty easy to identify. You have two numbers for y, two numbers for x. This is definitely a rectangle, right? You can also interchange the order of integration, interchange dx, dy with no problem. So we can look at one of the orders and see what we can do. So finding the antiderivative of essentially this guy is equal to x to 1/2 multiplied by y to minus 1/2. All right? If you want, you can write it in this form. So y is the constant. X is the only variable if I'm looking for this integrating, right? So what's the antiderivative for this guy? So I did a raise powered by 1, which means it's going to be x to 2/3. But also, when I bring down this power taken derivative, I'm supposed to have its reciprocal coming, all right? And then y to minus 1/2. Again, if you're not sure about the antiderivative, what you can do is to take the partial derivative of this guy with respect to x. So you take partial derivative with respect to x, to bring down 2/3. Now we cancel with the 2/3 in the front. And then this power will be exactly 1/2. All right? And then I'm evaluating from x equals 0 to x equals 4, and then dx, dy in the outside. Okay? So when x is equal to 0, everything is going to disappear. So when x is equal to 4, I have x to 3 divided by 2. That's going to give me 8, right? So 2/3, which is equal to 2 cubed. That's just 8, okay? So I have from 1 to 9, 16 divided by 3, y to minus 1/2 dy. Again, I stressed this in multiple times. I want to talk about it again. After I eliminate the interior integral, I'm supposed to have a function involving only y here. Okay? And then I'm trying to find the antiderivative for y to minus 1/2. I need to increase the power by 1. That is going to give me 1/2. But I have to be always careful about the constant here. I'm supposed to have 32 divided by 3 y to 1/2. Again, if you're not sure about your antiderivative, you take the derivative here, you bring down your power by 1, it's going to give you minus 1/2. And then you need to multiply everything by 1/2, that's going to give you 16 divided by 3. All right? So then I'm evaluating from 1 to 9. So this is going to be 32 divided by 3, 9 1/2 minus 1/2. So it's going to be 3 minus 1, in the end you get a 64 divided by 3. Okay? So this essentially what you need to do. This problem does not require any multivariable calculus at all. Essentially, if you look at this, every step is a single variable calculus. Okay? And you're dealing with these exponentials. So the only thing you probably have to be cautious about is these fractions and the powers appearing everywhere. Okay? Questions? Yep.
For the homework, there was a question that required the R, where you had to divide by the area of the section. What is that?
Oh, okay, so we'll discuss that later.
Oh, the average
Yeah.
value.
Yeah, we'll discuss it later. Any questions about this problem? Yep.
If you were to plug in the bounds for x, which is 0 to 4,
Mhm.
you actually end up with 64/3. Is that just like a big coincidence, or does that always work?
What do you mean by?
Like if you were to just plug in the bounds 0 to 4 from where you are here to how you got 64/3,
Mm-hmm.
like where you plugged in 1 to 9, where you have 32/3 y to the 1/2. If you plug in 0 to 4 there, you'll still get 64/3. Is that just a coincidence?
Yeah, it's probably just.
I'm a bit confused about what you're asking here. So
That's-
when I'm doing
Just
here,
don't forget.
so I'm evaluating the interior integral. It has nothing to do with y.
No, I know. I'm just saying if.
You're saying for the
I think it's
second
just a
integral?
coincidence.
For the
Mhm.
second integral with the y, if you plug in 0 to 4, you'll still get the same answer.
From 0 to 4, you're getting the same answer.
Where you have 32/3 y to the 1/2.
Oh, okay. Yeah, that's
That's
purely
a
coincidence.
coincidence.
Okay.
That's purely coincidence. Yeah. I can simply change this 4 to whatever number I want.
Got it.
It's not going to get the same answer.
Sorry.
Anymore. Right? That's a good observation, but unfortunately, coincidence happens. So second thing I want to talk about is so-called Y simple region. Y simple region where R is given by two numbers for X and two functions for Y. And the region looks like okay. So this is A, this is B, and this is what I call lower function G1. This is what I call the upper function G2, and this is integration. Okay. Okay, and once I can identify as a Y simple region, I can rewrite the integral from A to B from G1x to G2x fxy dy dx. Okay, so it's Y simple region, so I'm going to do Y integration first. Okay, so I have two numbers for X, two functions for Y, and the only thing you need to be very clear about is the geometric relation between the region and its boundary. Right? So this boundary is to the above, this boundary is to below. Right? So that's the lower function and the upper function. And we also have this X simple region where R is equal to Y is bounded by C and B, X is bounded by two functions, H1 of Y and H2 of Y. And in this case, I have two numbers for Y, so this is C and D, and left function and right function here. So this is the left, which is H1, this is the right, which is H2. And the region is bounded between these four pieces of curves, okay? And once we can identify this X simple region, I'm supposed to do the integration with respect to X first. questions?
Is there one where it's like combined with both, where you have like 4?
Well, this is the example where this region is both x simple and y simple.
Oh.
All right. There are plenty of opportunities we will see. There are plenty of examples where we will see a region can be identified by both, and indeed we have to identify it by both.
Okay.
Okay. So here's a very good observation, and this is exactly what we want to discuss next. So one thing we learned about rectangle, listen carefully. One thing we learned about rectangle region is that even though we can write it in 2 different integrating orders, sometimes one is much easier to compute. All right? One is much easier to compute because you want to find the antiderivative for you to regard. One is the variable, the other one is constant. The function will be completely different if you change the rows of the variables. All right? So in some cases, one integrating order is much easier than the other. Similarly for this as well. A region can be regarded as both x simple and y simple, but one of these 2 is much easier than the other. So we have to be able to identify a region as both types and then interchange them freely. So this is what we have practiced on Monday's class, but we're gonna practice a couple more, which is to interchange x simple with y simple. So y simple interchange with x simple. Again, I want to look back to that case. In the rectangle case, I can interchange this integrating order with no problem at all. I don't have to worry about anything, right? As long as I bring down this integrals correspondingly, then everything will be fine. Here is much more difficult, right? So if you want to change from the x simple, from y simple to x simple, originally you have 2 points for x. You have 2 functions for y, which are lower and upper function. I have to be able to transform all this information into 2 points for y and 2 functions for x, which are left and right function. Okay, so I have to be able to transform this information to that information backwards. Okay, and you can see these information are quite different, right? These 2 points for x and these 2 points for y. Okay, so in order to do that, usually you want to sketch the region. Like we discussed in Monday's class, when you sketch the region, you don't have to be very precise, but at least you have to be able to tell the geometric relations between the region and its boundary curves, right? You have to be able to tell this curve is indeed to the left of the region. This is indeed to the right of the region. You have to be at least able to tell the relations between the boundary and the region. And then you can identify which curve is lower, which curve is upper, which curve is to the left, which curve is to the right, all right? And then you have to represent these functions correspondingly. So these are 2 functions for y. I need to write down y is equal to a function of x. And these are 2 functions for x. I need to write down x as a function of y. So you have to be able to transform these functions back and forth. Okay? So sketch and then identify the region. So we will focus on how to do those 2 steps. And in terms of how to evaluate the double integral, I'm going to leave it to you. Okay? So evaluating the double integral, once you can write it down explicitly, it's all single variable calculus. Okay? So of course, the other step is evaluate the integral. 2 single integrals. So this is the very last step. So first, let's do this example. So I have 0 to 4, 0 to 8 minus 2x, fxy, dy dx. I want to write it as 2 single variable calculus right here, but with a different order. So this is the same region first identified as y simple region. I want to write it as x simple region. So the first step is to identify the region, which is draw to sketch the region. You don't have to be super precise, but at least you have to know where it is. So if it is a y-simple region, I have two numbers for x, right? Two numbers for x, which means x is bounded between 0 and 4 right here. Essentially, this region has to be bounded between these two vertical lines. All right? This line is x equals 0. This line is x equals 4. So your region has to be bounded between these two lines. Okay? And then I need an upper function and a lower function. Right? So the lower function is indeed y equals 0, which is exactly your x-axis. Right? So this is the lowest you can get in this region. The upper function is y equals 8 minus 2x. So this is a straight line passing through 0, 8 with slope minus 2. And it will indeed pass through this point. Right? So when x is equal to 4, y is equal to 0. So it will pass through this point as well. So this is the other function I needed. So this is y equals 8 minus 2x. And this is the y-simple region. I have the lower function right here, the upper function right here. So this region is going to be the inter-region region. Okay? So you have to be able to at least tell the geometric relation between a region and its boundary curves. This is the curve bounding from above. This is the curve bounding the region from below. So this is the only choice of the region. Because once you have a lot of curves, you have so many different pieces in the tree. You have this piece, you have this piece, that piece, that piece, that piece, that piece, that piece. You have so many different pieces. But you have to gather your information together to identify the only one and the unique one. This one, left is x equals 0, right is x equals 4, upper y equals 8 minus 2x, lower y equals 0. This is the only choice. Are you with me? You have to be able to draw, sketch the curve, and identify it is. Now I ask you this question. If I want to identify as an x-simple region, I need two numbers for y. Two numbers for, essentially I'm looking for the smallest value for y and largest value for y. Am I right? So there should be y equals 0 and y equals 8. Okay? So these are the two boundary values for y. Okay, two numbers for y. One idea is to just find the smallest